Good afternoon, everybody. First of all, I'd like to thank the organizers and the mathematics department for the chance to present my work in this event. And today, the title of my talk is Complex Systems with Uncertainty, How Can They Be Stable? And complex systems are systems that are basically made up of a large number of fundamental units, maybe molecules or neurons or individual people in a social system that interact to produce often surprising and difficult to predict macroscopic behaviors. And in particular, it's been a major area of scientific study over the last decades to try to understand and hopefully predict kind of critical changes in the behaviors of such systems. And it's kind of clear that we will need new mathematical insights and tools to tackle these problems. And in this talk, I will talk about how to generalize the kind of existing theory of stability from deterministic dynamical systems theory to systems that are affected by noisy fluctuations. And in the second part, I will talk more specifically about particular noise model, namely bounded noise, and how to work with it. And I will start with a story that I find useful in kind of talking about some conceptual aspects of stability. In the early 1700s, the King of Sweden commissioned a new flagship for his navy on the Baltic Sea. And this ship had a very ambitious design with 2 cannon decks, which was not completely unheard of at the time, but the engineers were slightly worried that this will severely affect the balance of the ship. But the king was eager to demonstrate his new flagship. And in fact, the warship Vasa set sail on the 10th of August, 1628. But tragically, it barely made 1 kilometer from the harbor when it actually met with some winds, and it quickly capsized and sank to the bottom of the sea. And so this is a nice example to kind of consider different aspects of stability, because of course the ship was to some extent stable at the shipyard. Otherwise they wouldn't have even tried to take it out. And I will look at these two cases here, namely Vasa at the shipyard and Vasa at sea, with some random perturbations. And I'll start first with the case of Vasa at the shipyard. So we model the stability of the ship with this kind of potential. And the idea is that there's a stable point, the upright position in the middle. And if you perturb the ship slightly, it will tend to return to that position. But then there is this kind of critical threshold that if you tilt the ship enough and even more, then it won't be able to straighten anymore, but it will capsize. And there was this kind of recent paper from 2013 where the authors, Jürgen Kurz and his collaborators, popularized this idea of basin stability. So what they suggest is that you can actually use the size of this basin of attraction as a measure of stability. And the popularity of this paper actually shows that there's a big demand for simple and quantitative methods for stability analysis. But the clear shortcoming of this is that it really only applies to this kind of static situation with no fluctuations. And in particular, even if you know that you have a large basin of attraction, it doesn't necessarily imply that you are very resilient against random fluctuations. So what people then usually could do to study stability under fluctuations is that you think of some kind of random process, perhaps like a Gaussian noise acting on your system, and you study stability. But of course, there's the fundamental problem that any unbounded noise, for example, Gaussian noise, has this property that for a positive probability, the system can receive an arbitrarily large random kick in an arbitrarily short time window. So this makes it clearly fundamentally unstable. But then the question is, does this actually matter? Because obviously the idea is that the probability of these large shocks is so incredibly small that it won't affect the practical analysis. But one could argue that in extremely complicated systems, nonlinear systems with multi-stability, it could make a difference. And in particular, if you want to study critical transitions or devise some early warning signals for critical transitions, you would need a conceptual, clear definition for stability. And in this context, there are several conceptual approaches for defining stability, but they tend to be rather technical, and there is no canonical interpretation of this thing at the moment. But in the meanwhile, so since the 80s, people have been looking increasingly to bounded noise as a model for uncertainty. And the interesting thing is that really, like, the surge of interest is on the applied side, and there's in fact very little work on this so far on the theoretical side. But we can try to see what happens if we apply bounded noise to this same situation that we studied earlier. And so with the idea is that the bound gives the maximal amplitude of the noise that you can experience at any time point. So if this maximal amplitude is 0, this corresponds to the base instability. But if you now increase the maximal amplitude, then your ship can kind of explore this kind of a limited range of angles around the equilibrium point. And there's this kind of well-defined boundary where actually the deterministic pull, the stabilizing pull, is exactly equivalent. It cancels out the maximal noise push to the other direction. And also there's a kind of critical value for this maximal noise amplitude, namely if the noise can push you up to this point, where actually the potential here, the second derivative of the potential changes sign, if you can push you up to that point, then it will be able to push you even further and you will destabilize. And it's interesting to note that this value here is nowhere near the kind of boundary of the basin of attraction here. But I also like to point out that there's a clear kind of cutoff between the presence and absence of stability in this case, which kind of connects this naturally to the classical stability theory in deterministic dynamical systems. And I call this the structural stability property. So if we now compare unbounded and bounded noises, it's clear that that one reason for people not using this bounded noise is that it really lacks the kind of general and rigorous theory that exists for unbounded processes, in particular Gaussian noise and let's say the stochastic integration and so on. And we don't typically have analytical solutions, which also implies that bounded noise modeling relies heavily on numerics, although the same could be said of unbounded noises as well. But there are some compelling reasons for actually looking at bounded noise as a model. And one of them is clear that it's a realistic assumption from the physical point of view. And then on the practical side, it admits this kind of unknown but bounded approach to modeling, which means that you don't necessarily need to know or estimate the expected value or the variance of your noise distribution. But if you know the bound for your noise, you can already work with that and do kind of worst case scenario analysis with that. And so the question is now, if this bounded noise seems to kind of like be the best of both worlds approach, so it's like conceptually clear, works with the multi-stable systems as well as linear systems, and you can quantify stability. Why aren't we actually doing anything with it? Well, we are doing, people are doing a lot, but on the theoretical side, the question is, can we actually build some theory and some numerics to work with this? And we started looking at the bounded noise in this kind of a case of discrete time dynamics. So the idea is that you have a deterministic map F, which depends on parameters, and you map the current system state forward with this, and then you add some kind of random kick, which we assume to be bounded, and this upper bound we denote by epsilon, and then you get the next state of your system. So it looks like this: you map your system state deterministically, then you know that your noise can only kick you so far from that point. And actually what we can do is we can consider all the possible noise realizations at once, and we get all the possible states where you could end up. Then we can map these forward and again add all the possible noises and get another set. And that's why this is called set value dynamics approach. And it corresponds to this unknown but bounded method that I mentioned earlier. And the stable sets in this setup appear as minimal invariant sets. So they are invariant under this dynamics. And it looks like that when you map a minimal invariant set forward deterministically, it kind of contracts within itself, and then you add all the noises and you get the same set back. And the question is, how do these stable sets now react to changes in the stability parameters or the noise of your system? And we did some numerics with the so-called Henon map, and you can clearly see this kind of abrupt change in the geometry of the minimal invariant set here. And it was shown 5 years ago, actually, that this kind of like a topological change in the minimal invariant set structure is always the hallmark of the bifurcation, a loss of stability in these kind of set valued systems. And this again relates to the structural stability property that I mentioned earlier. And so in order to understand this stability and these dynamics, we clearly need to understand the properties of the minimal invariant sets. And one of these is, of course, the geometry of the sets. So you can see that these sets are not always smooth. They can also have these kind of singularities. And in order to understand this, we actually looked at a more general problem. So for a compact set on the plane, you can look at the epsilon neighborhood of the set, and you can ask how complicated can the geometry on the boundary be. And then in this case, it turns out that either you are a smooth point, or then you belong to exactly one of these 8 categories of singularities. And we are now working to show that actually in the dynamics case, only these smooth points and these kind of wedge singularities appear in practice. And we're trying to get to submit a couple of articles from these findings, hopefully in the near future. And clearly, these things get more complicated when you go to higher dimensions, already 3 and 4. The picture could be more complicated. But another interesting aspect, actually, of these minimal invariant sets is that you can describe their dynamics by looking only at the boundary dynamics. So if you pick a point on the boundary of the minimal invariant set, we know that it maps inside. And we have shown that there's a unique choice of noise realization that actually kicks you exactly back again to the boundary of the minimal invariant set. And the cool thing is that if this map, the deterministic part of the dynamics F is differentiable, then we can find an explicit formula, an analytical formula for this point, if we take into account the tangential direction of the boundary of the minimal invariant set. And you can actually generalize this same idea to points that don't necessarily lie on the boundary of the minimal invariant set. And this gives you a way of actually kind of encoding some dynamical information about the set valued system, which is a priori infinite dimensional, to some finite dimensional dynamical system. And this is great because now we can use existing theory from classical dynamical systems theory to tackle the properties of these sets. And in particular for numerics, you can write down equations for fixed and periodic points of the boundary map and solve for these numerically to actually locate the boundaries of the minimal invariant sets. And that's not all, there are also indications that you can find maybe even early warning signals for loss of stability using this boundary map. And like a final selling point for this approach is actually that instead of just doing this kind of like brute force numerics by iterating the discretization of these boundaries of these sets, we can actually do smarter numerics using these theoretical insights. And so to conclude, the choice of noise impacts stability in fundamental ways, and bounded noise is an overlooked but promising option for looking at these systems, and set value dynamics is a good framework for this. So clearly, there are challenges. Main challenges are we want to build a comprehensive theory for bounded noise systems, efficient numerics, and hopefully look at early warning signals. And obviously, also in the near future, we also hope to do a proof of concept project with real-world applications. So in particular, if there's anyone in the audience who is working with applications and you think we could put our ideas together to make some progress, then please get in touch. Here's our bounded noise team at the Dynamical Systems Group. And with that, I'd like to finish. So thank you very much and hope you enjoyed.